In this video, we will learn about the different ways that atoms and ions can bond to form chemical compounds. We'll discover how the outer electrons, or valence electrons in atoms, are responsible for chemical bonding, and we'll learn how to depict this using Lewis structures. There are 118 different elements on the periodic table, meaning that there are 118 different types of atoms that make up all the matter in the world around us. Well, not quite, since some of the elements are man-made, but the point remains. But when we do look at the chemical composition of the substances that make up the world around us, there's another layer of complexity. We rarely see these different elements existing as individual atoms. Rather, we'll find that most substances are composed of atoms or ions of an element that are attached to each other by some kind of chemical bond. Chemical bonds between atoms or ions generally occur because the formation of a bond lowers the potential energy of the atoms or ions, which makes everything more stable. This is just like how if you release a ball at the top of a hill, it will roll down the hill and settle in a valley where its potential energy is minimized as well. There are three main types of chemical bonds that atoms or ions can form that generally depend on the types of elements we're dealing with. Covalent bonding occurs mainly between nonmetals. This type of bonding occurs when atoms share their electrons to form what we call molecules. Covalent bonding is a very common type of bonding you'll encounter in chemistry. For example, all the atoms in water are covalently bonded, as are all the molecules that make up the gases in the air, oxygen, nitrogen, and carbon dioxide, as well as most of the compounds found in living beings, like proteins, fats, and carbohydrates. The next kind of bonding is ionic bonding. This type of bonding generally occurs between metals and nonmetals. Ionic bonding is caused by an electrostatic attraction between oppositely charged ions. At the atomic level, these electrostatic attractions cause the ions to be arranged in a very orderly and repeating pattern that we call a lattice, which you can visualize like fruit that's nicely stacked up at the store. At the macroscopic level, compounds with ionic bonds usually form solids that are crystalline, like we see with NaCl, which you have at your house as table salt. Finally, we have metallic bonding, which, as the name suggests, occurs when we only have metal atoms. In metallic bonding, electrons are also shared, but in a very different way than what we saw in covalent bonding. In metals, the electrons flow around the metal atoms, which is often referred to as a sea of electrons. Unlike what we saw in covalent bonding, where the electrons are localized in a bond between the atoms, the electrons in a metallic bond are spread out throughout the entire metal, which we call delocalization. The fact that electrons are free to move around the metal atoms is why metals are generally great conductors of electricity. You noticed here we classified type of bonding by the types of elements that it occurs between, metals or nonmetals, which is generally enough to get us by. However, there are some exceptions to this. For example, BeCl2, or beryllium chloride, has a metal, beryllium, and a nonmetal, chlorine. But even though the bonding in beryllium chloride is between metal and nonmetal atoms, the type of bonding between the atoms is best described as covalent bonding, not ionic bonding like we'd expect. But exceptions like this are not generally the norm. You'll also notice that no matter the type of bonding, bonding always has to do with electrons. In covalent bonding, the bond is formed by sharing electrons between atoms. In ionic bonding, atoms gain or lose electrons to form ions, which are then attracted to each other. And in metallic bonding, the electrons become delocalized throughout the metal. Specifically, it's the outermost electrons that participate in chemical bonding, which we call valence electrons. The inner, or core electrons, typically don't participate in bonds because they are too close to the nucleus and they're shielded by the outer electrons. For main group elements, that is, elements in the S and P blocks, or elements in groups 1 and 2 and 13 through 18, the number of valence electrons is consistent on a group, so we can use the periodic table to determine how many valence electrons an element has. Magnesium is located in group 2 of the periodic table, so atoms of magnesium have 2 valence electrons, just like atoms of all other elements that are found in group 2. Chlorine is located in group 17 of the periodic table, so atoms of chlorine have 7 valence electrons. And since neon is located in group 18 of the periodic table, atoms of neon have 8 valence electrons. The number of valence electrons an atom has largely determines how many bonds it can form in the case of covalently bonded atoms, or what types of ions an atom can form in the case of ionic bonding. The scientist Gilbert Lewis pioneered many studies on the bonding behavior of atoms. He found that in general, when atoms bond, they tend to lose, gain, or share electrons to attain a filled outer shell. Since for many atoms that are main group elements, a full outer shell is 8 electrons, this behavior is often referred to as the octet rule. Now, this octet rule is just a rule of thumb, and it's quite easy to find elements that don't obey this rule. For instance, the first electron shell can only hold 2 electrons, so hydrogen and helium will have a full outer shell when they have 2 electrons. Boron also commonly breaks the octet rule. Even though it can accommodate 8 electrons in its outer shell, we commonly find it with less. And things get even less concrete once we get into the 4th period. Nevertheless, this is still a good rule of thumb for us to use when considering how atoms bond and form ions. With the octet rule in mind, let's take a closer look at some of these electron shell diagrams that we were looking at earlier. As we said, magnesium has 2 electrons in its outer shell. So if magnesium lost those 2 electrons, it could have a full outer shell, which is why magnesium and other elements in group 2 of the periodic table commonly form 2+ ions. Chlorine has 7 valence electrons, just like all elements in group 17 of the periodic table, which means that you'll commonly see chlorine gaining 1 electron, since it's only 1 electron away from a full outer shell of 8 electrons, which would form the CO- ion. Unlike magnesium, chlorine can also bond covalently with other atoms to complete its outer shell. Here, chlorine is bonding with hydrogen. I've left out the inner electrons in chlorine just for simplicity in this diagram. This would form the molecule HCl. Each atom participating in the bond shares one of its electrons, which completes the outer shell for both chlorine and hydrogen. Finally, neon has 8 valence electrons in its outer shell, which means that its outer shell is already full. This means that neon and other elements in group 18 of the periodic table won't tend to form ions or bonds. In other words, neon and other noble gases are unreactive. To depict how these valence electrons participate in a bond, we can use something called Lewis structures. Lewis structures, named after the scientist Gilbert Lewis, have quite a few names, like Lewis dot diagrams or electron dot structures, but we'll refer to them as Lewis structures in this video. Now, we could certainly continue to use the electron shell diagrams that we've been referring to throughout this video, but drawing the inner or core electrons over and over again when they don't really participate in bonding can be a hassle and can clutter the way of seeing what's really going on. So to draw a Lewis structure, we'll first write the element symbol of the atom or ion, which will represent both the nucleus and the inner electrons. Then we'll indicate the number of outer or valence electrons with dots. We'll place 1 dot at a time on each side of the element symbol until we run out of valence electrons. If the atom has a lot of valence electrons, once there is 1 electron on each side of the element symbol, we'll pair up the electrons and continue around until we run out of valence electrons. The dot placement here isn't important, just that we place 1 on each side before pairing them up. Looking at a Lewis structure can tell us a lot about the ions an atom will tend to form, or the number of bonds the atom will tend to form. When we look at chlorine's Lewis structure, we can see that 1 of the electrons are unpaired. This means that it can share that unpaired electron with another atom to form a bond, which is the conclusion we came with earlier when we were looking at the molecule HCl. And just like we were looking at earlier with the electron shell diagrams, the empty spot in chlorine's Lewis structure indicates that it can gain one electron to fill its outer shell and form the Cl- ion. And if we want to draw the Lewis structure for this Cl- ion, we would want to put brackets around the Lewis structure and put the charge of the ion outside the brackets. We can do the same thing for magnesium. From looking at its Lewis structure, we can tell that it has 2 electrons in its valence shell, which it will lose to form the magnesium 2+ ion. So determining the Lewis structure for an atom can tell us a lot of information. It can tell us the charge of the ions that it's most likely to form by seeing how close the atom is to having a full outer shell. And the number of unpaired electrons in the Lewis structure indicates the number of covalent bonds that atom can form. And just as an aside here, before we move on to some example problems, throughout this video we've depicted electrons in our diagram as dots, but electrons aren't actually dots centered around the nucleus. Their behavior is quite a bit more complicated than just simple dots. In reality, electrons are spread out around the nucleus in what's called an electron cloud. This electron cloud can take on rather funny shapes, but these dot diagrams are ultimately a useful depiction to help us keep track of bonding behavior. So now let's test our new knowledge on the types of chemical bonds with some example problems. Which of the following is not a type of chemical bonding? A. Covalent, B. Nuclear, C. Metallic, or D. Ionic? There are 3 main types of chemical bonding that we'll encounter in chemistry. The first is covalent bonding. This type of bonding is typically found between non-metal elements. It involves the sharing of outer electrons to create a chemical bond. When atoms bond covalently, they can form simple molecules like water, or they can form large repeating network covalent structures like graphite. Then there's ionic bonding. Ionic bonding primarily occurs between nonmetal and metal elements. This type of bonding is caused by an electrostatic attraction between oppositely charged ions. This is the type of bonding you see in table salt, which has the chemical formula NaCl, or sodium chloride. The final kind of bonding is metallic bonding, which, as the name suggests, occurs between metals. This type of bonding features electrons that are shared between the metal nuclei that flow around the nuclei like a sea of electrons. So as we can see, answer choices A, C, and D all refer to types of chemical bonding. Nuclear does not. Instead, it refers to a type of chemical process that generally results in a change to the nucleus of an atom. The valence shell of oxygen is the second electron shell and contains 6 electrons. How many covalent bonds can oxygen form? The valence shell is the outermost electron shell. The electrons in the valence shell are the electrons that are involved in the formation of bonds and ions. This is because atoms will typically gain, lose, or share electrons and bonds so that they have a full outer shell, which is typically 8 valence electrons. The problem tells us that oxygen has 6 valence electrons. But if the problem didn't give us this information, we would be able to determine the number of valence electrons using the periodic table, since for main group elements, the number of valence electrons is consistent down a group. Either way, since oxygen has 6 valence electrons, it will gain 2 electrons according to the octet rule so that it can have a full valence shell. It can do this by either forming an ion or by forming bonds. But this question specifically asked us about how many bonds oxygen can form. When atoms bond covalently, electrons are shared between atoms, with each atom that's participating in the bond giving one of its electrons to the bond. So each covalent bond that an atom forms will effectively make it gain 1 electron, so oxygen can form 2 covalent bonds, which is what we see in molecules that oxygen forms when it bonds covalently, like H2O, where oxygen is bonded to 2 hydrogens. Now let's finish things up with the key points for this lesson. Chemical bonding joins atoms together to form compounds. There are three main types of chemical bonds: covalent bonds, which typically form between nonmetal elements, ionic bonds, which typically form between a metal and a nonmetal, and metallic bonds, which form between metals. The valence, or outer electrons, are the electrons that are responsible for creating these different types of chemical bonds. When atoms bond, they typically lose, gain, or share electrons so that they can attain a full valence shell of 8 electrons. We can use Lewis structures to depict the valence electrons for an atom or ion by drawing the element symbol to represent the nucleus and core electrons, and dots around the element symbol to represent the valence electrons.